Howdy, we are looking at sections 2.1 and 2.2, which we're looking at inductive reasoning, we're looking at patterns as well as conditional statements. And so inductive reasoning is just a fancy way of saying these are patterns that we have observed. And then in looking at a conjecture, when we look at these patterns and observe them, we come to a conjecture, or it's just a conclusion based on these types of patterns that we see. For an example, when playing baseball, you might observe that the pitcher is always throwing a fastball on his first pitch. So your conjecture might be that, all right, I'm going to sit dead red on that fastball. So let's look at some examples. In looking at these things, this is going to be numbers 1 through 4 and 6 through 8 where we are looking at these. And so in number 1, we're trying to see what's going to come next, what's happening in this pattern. So if I go from 4 to 7, how can I do that? Well, I could add 7 to that. And so the next one is to see, does that, in looking and observing this, does that come to a conclusion here? And then I add 7 to 11, I get 18. I add 7 to 18, I get 25. So here I can conclude, or my conjecture is that the pattern is falling by adding 7. So I continue to add 7, and we are done. Same thing with number 2. We're trying to look at what we can observe and then make some kind of conjecture or conclusion from it. So how do I get from 25 to 5? I can subtract 20, but does that work from 5 to 1? No, it does not. And so then I'm like, all right, well, how can I get from 25 to 5? I can divide by 5. And then I can divide 5 by 5. I get 1. And then I see that, okay, now I see the pattern. So I'm dividing by 5 or I'm multiplying by 1 over 5. And that's how I find the rest of the sequence. In this next one, I look, how do I get from 17 to 15? And I go, oh, I am simply subtracting 2. And then can I subtract 2 from 15? Yes. Subtract 2 from 13? Yes. And I continue. Here we're looking at patterns dealing with letters and dealing with our vowels here, A, E, I, O, U. Also a good thing to do as you're looking at all of these types of things is simply to press additional problem or similar question. That way you can kind of get lots of different examples. And then in number 5 is the first time we're kind of looking at counter examples. Teenagers are excellent at this, and this is where you're trying to find something wrong or something that is false, leading the conjecture to be incorrect. All right, and all you need is one counter example to prove that it is false. If the name of a month starts with J, then it is a summer month, and you might go, aha, January. It starts with a J, but it's actually in the winter. All right, so that's exactly what we're looking at here. And so in this one, we want a counterexample. So angle 1 and angle 2 are supplementary. So this means that they add to 180 degrees. So one of the angles is acute. So we need to find an example where two angles add to 180. That means and proves that they're supplementary. But can that happen where we have angles that are not acute? And so this is an example. 90 plus 90 is 180, so that satisfies the supplementary. But 90 and 90 are not acute angles, they're both right. Once again, we're looking for patterns here. We go, how do we get from 4 to 7? I can add 3. Add 3 to 7, I get 10. All right, so let's come back here. I added 3. What did I add here? 7. I added 5 here, so I had 3 and then 5, maybe 7. Hello. All right, then I had not 7, but I add 9. Hello. I add 11. Oh, yes. And then I'm adding 13. Number 7, we're giving this and we're trying to predict what's happening. So we're trying to prove, is this conjecture true or not? And so we look at this first statement here. We have 4 times 9 minus 1 is 35. And then we have 54 times 9. So we see that we are always multiplying times 9. We see that we're always subtracting by 1. And we're changing this initial number here. So from 4 to 54, from 54 to 654, then we start to see this pattern. So we had 4, and then 5, and then 6, and then 7, and then I believe to be 8. So that's what's happening with this number. And then we're looking at our solution or our conjecture, and we're trying to see, is this going to follow the same pattern? So at first we had 35, the 3 changes to a 4, The 5, as we can see on the outside here, stays the same, and we're starting to add 8s on the inside. So this 3 becomes a 4, then a 5, and a 6, which thinks it will be a 7. I first had 1 8, then 2 8s, then 3 8s. I think it will then have 4 8s, and then this 5 remains the same on the outside. We see that that is indeed true. Looking at more patterns here, so I say I'm alternating between a triangle and a square with a dot and a square without a dot, and that means I should end up with a triangle there. And here, and looking at number 9, now we're starting to look at conditional statements. What is a conditional statement? So conditional statement is just our if-then statement. So if the sun is shining, then I am happy. So that is what we're doing. We break this down into its 2 parts. Whatever follows the if will be our hypothesis. It follows the if. And then whatever follows our then is our conclusion. And so we can also look at this as a Venn diagram. Our conclusion includes our hypothesis as well as other options, all right? And then in looking at it in symbols, we're looking at our P, our hypothesis, and then it leads to our conclusion, our Q. And so now we're looking at this. I've highlighted it for you so we can see our hypothesis is here in yellow, and it's everything dealing with our if. And then everything in green here is dealing with our then, and it is also dealing with our conclusion. Same with number 10. Our hypothesis is everything with the if, and then is dealing everything with our conclusion, our then. As well as here, we're not changing our if or our hypothesis, right? So in these first 2, we changed that. They actually solve for it. So we're not trying to change this. We're not trying to solve it. We're simply trying to write a conditional statement, which is an if-then statement. So as you can see, these things have not changed. And then here, we're simply trying to write it as an if-then statement. So if 2 statements have the same truth value, then they are equivalent statements. And then now we're looking at a Venn diagram, and we must look here. I tried to put it in green here. So the athletes is talking about our conclusion, and then the hockey players is talking about our hypothesis. This also happens in number 18. All right, so our sophomores, this is our conclusion, and our if then, this is our hypothesis. And so now we're looking at counter examples, what we talked about earlier. And so if you live in a country that borders the United States, then you live in Canada. So we can see, well, this is false because there are different countries that border the United States. So I could also live in Mexico because that also borders. And then if you live in Canada, then you live in a country that borders the United States. Notice that it doesn't say only borders. So this is true, all right? So in 16 and 17, they're breaking these things into parts. So now we're looking at conditional statements. And so the conditional statement is what we talked about earlier. This is where we have our hypothesis and conclusion. So the converse, the inverse, and the contrapositive are all going to do something to this conditional statement. A converse is going to exchange the hypothesis and the conclusion, and you see we just changed that. So whatever was the conclusion now becomes after the if, and what was the initial hypothesis now comes after the end and is now our conclusion. So we're looking at our conditional. If I am in Michigan, then I am in the north. So I'm simply exchanging that order of things. If I am in the north, then I am in Michigan. So that's all we've done here to write the converse of that statement. So now we're checking, is that converse true or false? And so in this particular case, it's false. All right, it says I'm in the north, then I'm in Michigan. Well, I can be in Wisconsin and still be in the north. So now we're looking at the inverse. And that inverse, as we can see, it is going to be in the same order as our conditional statement, except we are going to negate both the hypothesis and the conclusion. And so if we look here, it's going to be in the same order, Michigan and North. But if I am not in Michigan, then I am not in the North. So that's the addition here, making it's the inverse. And now we check our truth value of that inverse. So if I am not in Michigan, then I'm not in the North. And this is false because I can also be in Michigan and still be in the North. So simply not being in Michigan doesn't mean you are not in the North. Now we're going to look at the contrapositive. Contrapositive, so this is going to be in the same order as the converse, and we are going to negate the hypothesis as well as the conclusion. So the contrapositive, we're keeping, if I am not in the North, then I am not in Michigan. So this is, if we look at the original statement, so we've changed the order and we have negated. That is our contrapositive. And so is this true? If I'm not in the North, then I'm not in Michigan. So this is true. We're going to repeat these same things for another example. And so odd natural numbers. So natural numbers are just numbers starting at 1 and going on. So these are whole numbers, 1, 2, 3, 4, 5, 6, 7, and so on. So we're looking at odd, so this is looking at 1, 3, 5, 7, 9, and so on. And then prime numbers. These are numbers that have, the only numbers that go into it are itself and 1. So examples of that are 2, 3, 5, 7. So 9 is that first odd number that is not prime because 3 also goes into it. And so we're simply just writing an if-then or a conditional. So if an odd number is greater than 7, then it is prime. So that's all we're doing here. And then we're determining the truth value of this. And so this would be false because the odd number 15 is greater than 7, but it's not prime. So this is saying, if we look here, if it's an odd number greater than 7. So we found a counterexample. So 15 is an odd number greater than 7, but it is indeed not prime. Now we're going to do the converse, and see here, converse, and this is where we're going to just simply change the order. So we change the order of that. If a number is prime, then it is an odd number greater than 7. So we've just changed the order of the original conditional. And so now we're looking for a counterexample. If a number is prime, so we pick a number that is prime, but it isn't an odd number greater than 7. It's obviously smaller. Now we're going to look at the inverse, and looking at that inverse, we're simply going to be keeping the same order as the original conditional, and we are going to negate the hypothesis as well as the conclusion. And so we have here, if an odd number is not greater than 7, then it is not prime. So we're going to try to find a counter example to this, and this is the number 3. 3 is an odd natural number not greater than 7, but it is prime. So it has to also not be prime. So that's what happens with this particular one. And then our last one is the contrapositive. And here's where we're dealing, it is in the same order as the converse, or we've switched the order of the conditional, and we have also negated the hypothesis and conclusion. And so for this one, if a number is not prime, then it is not an odd natural number greater than 7. So we need a counterexample for this, and that is 15. 15 is not prime, but it is an odd natural number that greater than 7, so it doesn't satisfy that here.